I have been building low-cost mobile robots for about the last 7 years and have always wanted to experiment with localization. Localization systems, which identify the position of a robot in its environment, are essential for most mobile robotics applications. Last summer, I started tinkering with tracking the position of some LEDs using webcam. I did a bit of napkin math and thought that I could use a rigid LED structure with remote control to calculate the position of a rover in 3D. I originally estimated it would probably take a weekend or two. It wound up being my capstone project. We decided to call it Project Firefly. As far as I can tell, this is an entirely new method of localization. All comparable systems rely on using multiple cameras for depth, whereas we use the lantern, our structured array of LEDs. Many people we were talking to expressed admittedly reasonable concern that my math had too many degrees of freedom and the system would not reliably converge. That's why I decided to make this video, to explain how Firefly works and why I'm so excited about it. To demonstrate the operation of the system, we decided to build a small, low-cost rover that navigates using a lantern. Our project has 4 main steps. The first is the data intake, which reads images from the camera and identifies each LED in frame. The second is position calculation, which uses these readings to identify the rover's position in 3D space. Third, we have navigation, which uses position data to generate commands for the rover. And finally, we have steering calibration, which uses some simple machine learning to learn how to more efficiently steer the rover over time. The data intake process activates and photographs each LED. These images are processed to calculate the precise angle of each LED relative to the camera. Our first step is to adjust for lens distortion. We use the OpenCV2 checkerboard pattern to calibrate the camera, which eliminates lens distortion and finds the field of view of the camera. The LED spot is immediately obvious in this image. The poor contrast bandwidth of low-cost webcams causes the LED to completely blow out the image sensor. This is usually considered a drawback of cheap webcams, but is actually quite helpful here, as the bright spots are more easily detectable. Although the system can operate by simply checking for this bright spot in each image, consistency and precision can be improved by comparing multiple photos. We can subtract each image from the next, identifying the area where brightness increased, rather than just finding any random bright spot. Finally, the center of the bright spot is calculated. Using the calibration data, we can convert this point in the image to an angle, indicating the bearing of each LED relative to the camera. These values, along with additional metadata, are recorded and the process repeats until every LED has been tested. There are several dynamic feedback elements that catch errors and improve accuracy. The brightness of each LED is adjusted in real time, adapting to lighting conditions and minimizing reflections. The order of activation is also determined algorithmically. LED spacing is important, as adjacent LEDs can have overlapping bright spots. Each LED can also be measured multiple times, as its brightness is tweaked to be visible. Reflections are another common issue, so each output image is checked to ensure there is only one bright area. This also provides resilience in case of interference from other light sources, as any external blinking lights will register as a reflection. If any errors are detected, the data point is tossed out and the LED is retested. When all LEDs are identified or dropped, the data is passed over to a separate thread for processing. Instead of calculating the distance directly from the image data, Firefly considers the set of sight lines from each LED to the camera. These lines each pass through one LED and converge at the position of the camera, which we place at the origin. From our 3D model of the lantern, we know the relative position of each LED to the center of the rover. In this visualization, each blue point represents an LED, and each black line segment is a section of a sight line from the camera. Using an optimization algorithm, we iteratively generate and test different positions and rotations of the rover, moving the point cloud around in 3D. Error, shown by the red line segments, is calculated as the average distance squared between each LED and its corresponding line. We can observe the current best estimation improve over time. This system consistently converges on the correct position with a squared error of less than 1 mm per LED. For demonstration purposes, the rover was programmed to loop through a set of waypoints. The rover is initially placed at each target waypoint, automatically finding and saving its position. The navigation algorithm reduces the location data to 2D, using only the XY position and Z rotation relative to the starting waypoint. The current position is compared to the target position, and the required rotation and distance to the waypoint are used to calculate the required motion. This plot shows the results from a consistency test, in which the rover repeatedly moved through 3 waypoints. Each hexagon is a point on the floor where localization was completed, with a line connecting it to a previous position. The colors range from black to orange with recency, and the green hexagon represents the current target position. In this image, the rover ran for over 3 hours without intervention. The only deviation, the path which cuts through the center, is from the rover starting from a random position. To minimize costs, the rovers do not have sensored motors. This lack of feedback means that the motion control only has 3 inputs: which direction to turn, how long to turn, and how long to drive forward. Early versions relied on simple, hard-coded relationships between drive durations and motion. Unfortunately, factors such as battery voltage, floor friction, and motor wear mean that these relationships can shift over time. This makes the rover gradually stop moving correctly. I realized that by comparing the start and end positions of each move, we can calculate the actual rotation and distance resulting from each motion command. This was a perfect problem for a simple machine learning system. Initially, the rover moves using a predefined, intentionally undertuned equation, moving slowly but safely and recording each move. When enough motion data has been recorded, the steering algorithm is replaced by a line of best fit through its recent motion history. As you can see in this graph, the turn duration is calculated from the angle change, and the drive duration is calculated from the distance to the waypoint. Right turns are calculated as negative durations. Despite its simplicity, the system massively boosted rover performance, which observably improved in just 15 minutes of training. There are a ton of features and optimizations that I didn't have time to implement, so I'll likely continue experimenting. There are several other interesting position calculation algorithms I wrote that didn't make it into the final system. I would also like to implement some more sophisticated machine learning methods. Finally, I would quite like to eliminate the need to stop for measurements by using either RGB LEDs or image timestamps. As is, Firefly is one of the cheapest localization techniques available right now, and I'd love to see what other people can do with it. Everything is open and free to experiment with on GitHub. There's also more information available in our final report, which I have linked below. As always, please shoot me an email if you make anything cool with my project. See you next time.